Spooky Halloween.
Ooh.
I'm so excited. This episode comes out on Halloween. And so we are going to be chatting about something fun and spooky and Halloween themed. Kind of nostalgic. That's been my Halloween vibe lately, is nostalgia.
This is going to be scary.
Not too scary.
Okay.
It's like sort of like about the absence of scary. It's like Halloween is darky and spooky and gloomy.
Uh-huh.
And then there's an eerie light sometimes that comes from glow in the dark things.
Yes.
And that's what we're going to talk about. So it's kind of spooky, but also it makes it less scary because it's not dark anymore.
Okay, nice.
So we're going to talk about what is the glow in the dark light. And there's even some forbidden spooky chemistry. And that's literally what it's called. There's a forbidden thing in the chemistry world that happens for this. And it's a little bit of physical chemistry. And if you ask any chemist what the hardest chemistry, scariest chemistry is, they'll say physical chemistry.
Dang.
So we're getting into it.
Wow.
We're getting into the spooky chemistry of it all.
Wait, what kind of chemistry is the scariest kind?
Physical.
Ah!
That's so dumb. All right. Are you ready to do this?
Let's do it.
Okay, you ready?
Yes.
I hate you so much. Hey, I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
Spooky edition. We didn't plan to say that.
No, we did not.
Oh, you're so good at that.
It's like the only really good sound I can do. And actually, you know what, the playground...
And it's only useful one time a year.
Right. Actually, I do get to practice it multiple times a year because there's a playground near my home where I take the kids, and there actually is like one of those little like sound board kind of things. It's like, I don't know how those things how they're weatherproof, but they are at the playground where you can press some on some different animals.
Yes, yeah.
And there's a wolf, and it sounds just like that. I'm like, yes. Like,
it's almost as if they recorded you.
yes. Or maybe that's not really how wolves sound, and it's just a bunch of people like me making this sound. It's more of a human sound.
Yeah.
I've never heard a wolf sound like that.
Me neither.
I've only heard the sound effect, so who knows?
I wish I had a good Halloween
yeah.
a spooky witch sound or something,
Yeah.
you know?
Yeah.
You know that spooky witch in the 90s that you walked by and it made that noise?
Yes. Oh, yes, I remember for sure. Yes.
Very nostalgic.
Yeah.
Okay, so speaking of nostalgia, let's do a, big picture, glow in the dark. What are they? And then I'm going to get into more of the chemistry and then even deeper in the chemistry.
Okay.
So just to go really big picture, glow in the dark things are really just molecules that have absorbed energy in the form of light.
Mm-hmm.
And then they just release that energy also in the form of light slowly.
Okay.
And it's just weird because we're used to things that either reflect light off, they don't re-emit the light really, or we're used to things that maybe they're fluorescent, which means when you shine light on them, they immediately emit the light back, like fluorescent markers and things. They're absorbing and re-emitting light just immediately. So if you take the light away, you take away the fluorescence too.
Right. I see. Okay. Yeah.
But all that's happening that's different about glow in the dark is that it absorbs the light and then their energy releases so slowly that's why it shines after the immediate source of energy. The light is gone. So and that's kind of special because it's just rare. Things don't usually release light like that.
Okay.
So that's your quick 10-second. If I was on the elevator with you and I needed to explain what glow in the dark was, I would just say that. Oh,
Okay.
It absorbs light and it re-emits it slowly.
Got it. Okay.
But I feel like that kind of takes away some of the really cool things that are happening. So I kind of want to dig a little bit deeper.
Okay.
Okay, so typically when energy in the form of heat or light, is absorbed by something, that thing is usually going to absorb the light or the heat. It absorbs the energy. And when the energy is absorbed by a molecule, we've talked about this before, but electrons will get excited. So just to, I guess, think going back even further, molecules are generally made up of atoms. And atoms are surrounded by electrons, different numbers depending on the different atoms. And so if energy is absorbed, those electrons, we call it get excited.
Okay.
And we've often used the analogy of like a little kid that you give it energy. It like starts to, kids start to move around a lot more. Or we've used an analogy of like a ladder. If the electrons are given energy, they go up to these higher levels and then they release energy to come back down. So, or like, then I have like a better energy analogy is like, oh, they absorb energy and they hold on to, like if they were climbing up a rope, and then when they're like tired and they let go of all the energy, then they fall right back down to like what we call the ground state, where they're just like not excited. They're just like normal.
Okay.
So that's sort of the chemistry language behind it. But I'm going to sort of expand that analogy for what happens in glow in the dark things. Okay, so now imagine that instead of you just like climb up this rope and then fall back down, you climb up a rope or a ladder, and when you run out of energy, you come back like to a platform. And then when you run out of the energy, then you fall back down the same way you came up. Okay, so that's what we typically see. And if it emits light, it happens right away. You climb up, you get to the platform, you fall back down. But if I change that to you climb up, you get to the platform, and now you have to find a different way down. You can't come back down the same way you came up. You have to find a different way you came back down. It's going to take you longer to get down because you have to find this pathway. You have to find a new way. And I'm going to make it even more complicated and say like there's a stairway, but it's hidden.
Okay.
So you have to find the hidden pathway to get to where you need to go, and then you can come back down.
Got it. Okay.
So that's kind of what happens if you were to have a bunch of electrons in something that's glow in the dark. They absorb energy, and then instead of just falling right back down, they absorb energy and they get trapped sort of on this platform. And they're told, okay, you have to find the secret passageway to come back down.
Okay.
And you can't tell anyone else when you find it.
Okay.
So instead of everyone climbing up and then coming right back down, instead everyone climbs up and then they're all just milling about up there. And then one by one, slowly they're finding the pathway and coming back down.
Okay.
Okay. So that is essentially what's happening in glow in the dark things is these electrons get excited. And for reasons I'll talk about in a minute, they basically get trapped in the excited state.
Okay.
They have to find a secret hidden way down out of the excited state. And that takes a lot longer. So like we're talking for instantaneous, it happens in like 1 times 10 to the negative 12 of a second.
Okay.
So like, what is that? One millionth of a second or something like that.
Okay.
But these things will happen instead, like on the order of seconds, because the electrons are taking so long to find where they need to go and come back down.
Right.
So it takes much longer. And it's also not happening all at once. You know how brightly something fluoresces?
Yeah.
But then the eerie glow from glow in the dark is like sort of a lower glow. It's less intense.
Right.
That's because you're just getting a few electrons falling down every few seconds or every, fraction of a few seconds.
And it's so faint, you can't even tell it's happening until you've already removed all the other light to see it. Like,
yes. Yeah. Like,
it just isn't really obvious unless you've like made other light go away so you can actually see.
Yes, because it is still glowing even if the lights are on.
Yeah.
Yes. So that's kind of like the electronic of what's happening. Another thing I thought of is, like when you have a celebration at like an event and you have all the balloons up top and then they all fall down at once.
Yes.
That's like fluorescing. But if you were, say, to just make like one little slash in the net that's holding it up and they can only trickle down slowly, little by little, it's going to take you like hours for all those balloons to fall instead of them all falling down within like a minute.
Right.
That's similar to what is happening with these electrons. They get excited and normally they just come back down really quickly. But in glow in the dark things, they get excited and they get trapped there and then they're just falling down one by one. So they're coming down much slower.
Yeah.
So that is the chemistry of glow in the dark. I'm going to talk about it a little bit more, but that is the phenomenon itself is actually called phosphorescence. So when you've seen things be fluorescent, fluorescence is the like property of absorbing light and immediately emitting it.
Okay.
Phosphorescence is absorbing light and then the light, the electrons getting trapped in that excited state and the light slowly re-emitting.
Got it. Okay.
Okay. So, but now the question is, why do they get trapped in the higher state?
Yeah.
So that's different.
Yeah. Why do they get trapped in the higher state?
Why do they? So I think this is kind of
Wait, is there phosphorus involved? I'm like phosphorescent. Like, why would it be called that?
There is I had it written down, but I can't find it on my page.
Sorry.
So yes, there is a phosphorus compound that has this quality, but the most common phosphorescent molecule that we use now is actually called strontium aluminate, and it has some impurities in it, which is why it can occur the way that it can. But I do think phosphor was the original one. I read about that, and I planned this a little bit ahead of when we're actually recording it, and now the phosphor fun fact is gone from my brain.
It's okay. I was just curious. I was like, they better have named this.
Yes.
Because of that, at least a little bit. Okay,
yes,
good.
phosphor was involved. Yes.
I'm happy.
Yeah, I'm pretty sure. Okay, so the reason they get trapped in this higher state, I think this is the most confusing part, but electrons like to hang out in pairs, and these pairs have to have opposite. It's really like magnetic pole kind of, but it's like it's described as spins. So you can imagine one is spinning clockwise and the other spinning counterclockwise, and so they're like angular momentum is opposite. One goes up and one goes down.
Got it. Okay.
It's like this sort of. So they have to be in pairs, and one has to be spinning in such a way that it's spinning, quote, up is what we would say. It's like it's got this particular momentum going one way versus the other way.
Okay.
And so they have to be in pairs like that. So typically when an electron gets excited, say, and you've probably done this in general chemistry class. Did you ever draw those little one arrow up and one arrow down in the like orbitals? Do you remember drawing that?
I don't remember that, but it doesn't mean we didn't do it. I just, now that has been 10 years ago. So
even in high school chemistry, sometimes you'll have to do it where it's weird because
longer,
it's like, it looks like half an arrow.
Oh yes. That does sound familiar.
Okay. So half an arrow is one electron in chemistry.
Okay.
So if you draw like half an arrow pointing up and then the other half arrow pointing down, do you remember doing that?
I can see it in my head. That doesn't mean I really remember anything else about it, but
okay, that's
I'm
fine.
Sure,
that's fine.
We did. Yeah,
that's all you need to know. Usually they come in pairs like that, where it's like usually one arrow pointing up and one arrow pointing down. And when they get excited, the one arrow should stay pointing up and then come back down and stay pointing down.
Got it. Okay. Okay.
So that's what should happen. And when it's like that, it happens really quickly. It's easy to go up and then it can come right back down to where it came from and sort of go back to where its little buddy or pair.
Okay.
But what can happen is that sort of on the chemical level, when these electrons get excited, there are like, you can think of a lot of electrons in the excited state, and they may bump into some other molecule or some other atoms floating around or something like that. And that might cause you can think of it as the electron to flip around.
Okay.
So if it was pointed up, now it's suddenly pointing down.
Okay.
And then it can't come back down because then it would be next to another arrow that's pointing down. It's not with its perfect pair anymore.
Okay.
So I try to think of it as like it was hard for me to think of a good analogy, but like if you had a spot that was like just right, just for you, and then you leave and for some reason you can't come back to that spot.
Okay.
The analogy that just came to my mind was that movie Pearl Harbor, where like the one guy goes to war and then the other guy starts dating his wife or whatever. And then when he comes back, there's nowhere for him to go because she's taken. I don't know. I can't think of something.
Yeah.
Or maybe like when you have a sibling and you get up to go to the bathroom, if you don't say like, I get my seat when I come back, they steal it. There's nowhere for you to go back. Yeah. And then instead of you just coming right back to your seat and sitting down, there's a hole to do.
Yes.
It's sort of like that. The electron that's pointed in this certain direction gets excited. And then while it's up in the excited state, it bumps into something else. And that bump causes it to like release a little bit of energy, but not enough to come all the way down. And it flips over.
Okay.
So it literally gets like knocked off course is kind of how you can think.
Okay.
And then once it's knocked off course, it can't go back to the spot that it came from because it has to be flipped a certain way.
Right. Okay.
So that transition where it goes from being flipped, the wrong way back into the spot where it doesn't belong is called a forbidden transition.
Okay. And what did you say caused that flip again?
If it's like when it's in the excited state, it could interact with other molecules or something. So it could lose a little bit of energy and that could cause it to sort of get knocked off course. It's maybe how you can think of it.
Okay.
It's kind of confusing that it happens.
Okay. It's called a forbidden transition.
No, the flipping originally is, it's called going into a different state.
Okay.
For chemists, you might know it's called singlet and triplet state, but that doesn't matter.
Okay.
So it goes from the state it's supposed to be in to the opposite state.
Okay.
You can think it goes from up to down and then coming from the excited state, but you're flipped the wrong way, back down to the ground.
That's called forbidden.
That's forbidden.
Okay.
Maybe it's like a breached birth. It's like harder to have a birth if the baby's head isn't pointed down.
Right.
If the electron is pointed the wrong way when it's up there, it's not going to have an easy of a time coming back down.
Got it. Okay.
It's just flipped the wrong way.
I love that somebody naming it called it forbidden. I'm just like,
I know.
It's so funny because it's like, electrons don't really care whether we're forbidding it or not, honestly.
I know.
Like, it's happening whether we're going to allow it or not.
I know. And I was like, ooh, it's forbidden. It's like secret and scary and against the rules.
But you know what's cool about that? Because for Halloween, it almost sounds like it's a curse in some way. It's like, whoa, guys.
I know.
Y'all didn't touch the forbidden amulet, did you?
The forbidden transition.
Yeah,
Yeah, spooky transition. So the transition of it coming back down, the way it was explained to me in school, and I'm not sure if this is 100% right. It was hard to find something that like sort of backed it up, is it has to flip back into the right position as it's sort of traveling down.
Okay.
So instead of just like, being excited, pointed up, staying pointed up, coming back down, pointed up, it gets excited, pointed up, it flips to be pointed down, and then for it to be able to come back all the way back to the ground state it was in, it has to go down and it'll flip in transition back to being up.
Okay.
And that's forbidden because it's just harder and more rare for it to do. And when we think of it, it's like harder, slower, more rare, because normally electron transitions happen in what we call like femtoseconds. So it's like, really, really, really small fractions of a second.
Okay.
So these take 1 or 2 or 3 seconds, or like orders of magnitude. So it can take like 1 second, 10 seconds, hundreds of seconds for the light to come back down.
Okay.
Chemically, that's like a really long time, but for us it might be just like 15 minutes, and that's why things glow for like 15 minutes. Some depending on the material, they can maybe glow longer or less time.
Okay.
And that's it.
Wow, that's so weird.
I know. It's just like what you see a lot of electrons excited and then coming back down, but they just get locked in a room and they can't come down until they find the secret forbidden passageway.
Yes.
And have to come down a different way, and that takes them longer to find, and so then they only come down one at a time, and so they just give you a little bit of light for longer.
That's so interesting. And so it has to do with the fact that these specific atoms that are having these electrons doing that. It's not just happening with any old atom you pick out of a bag. It's like this specific molecule you're talking about, right? This like this impurities with the whatever it's called stuff.
Yeah, you basically need like a sort of a special quality, which is like this is like getting a little bit more in depth, but the ground state, it's like it has like tiny little layers within each layer. So if you're like, if you're not at once you get to the excited state, there's lots of little layers in the excited state that where the electrons, like they get excited all the way to the top. And then they sort of, the vision I always have in my mind is, those like pinball machines where you like shoot it up to the top and then it has like those little pegs and it sort of slowly comes back down and then it might get to like a big drop down. It sort of does that where there's like little levels within the larger rung that it gets excited to. And then sometimes there's like, this is so hard to try to describe. You can sort of build in extra little levels within those levels by adding like impurities or other things. And the way that those levels line up is if the molecule or like while the electrons are in the excited state bumps into something else so that it can just let off just the right amount of energy to like flip over into those other little shelves that we've built in, then that's how it gets to where. So you have to like have your molecule engineered well to do that. So there's just certain things that have that quality of being able to do that. It's very unlikely, which is why it's called forbidden. It's just really rare. And it doesn't happen unless you like sort of get all these factors just right. So two common ones is strontium aluminate with some impurities of another material, europium or dysprosium. I don't even know how to say that. Or zinc sulfide. And zinc sulfide is often used in glow-in-the-dark face paint, which is often used on Halloween.
Right.
So
nice. It's kind of reminds you of too. Like it's not like we need a lot more analogies because your analogies have already been really good and helpful a lot. It popped into my mind thinking about. I've kind of always been fascinated with outer space ever since I was a kid. One of the things that like I remember at one point learning that I was like, oh duh, that's like crazy. It also makes it even more impressive the way that like astronauts, cosmonauts, all the different people figuring stuff out. Whenever you go somewhere, say we plan a trip to Mars, Earth and Mars are in one position. When you leave Earth, both Earth and Mars are still moving. Yeah. You usually try to plan to get to a planet whenever things are the best scenario where you can get there quickest. But guess what? Depending on how long you're there, when you want to leave, your route back could be like way longer. Yeah. Because it's like, oh yeah, it took us 3 months to get to Mars. But if we try to leave right now, it actually take us twice as long to get back. Yeah. That's just I'm spitballing. That's not accurate really, but like something like that could be the case.
Yeah, like it shifts over in its orbit. Yes. And so now it's like on the oblong part.
Things moved and it's just, and it's like a totally different trip now. It's not the same at all.
Yeah, that is a really good analogy.
But I was just trying to think of like from the perspective of the electron that this is happening to or whatever. Of course, it's a little bewildering, I'm sure, if they could, But it's like,
from the
wait.
perspective of the electron, I love thinking about that.
Because like that's what's got to be so weird about like we all feel like we're fixed in a place, but we are not. Yeah. The Earth is spinning always and also rotating around the sun. And guess what? Our whole galaxy is moving. So it's like,
that's crazy.
Actually, everything's moving. So it's like, I thought I just went over here, but I guess for some reason now I have to go like do a different way. Yeah. And it's got to be odd, Yeah. But like, just like us, we would be like, what happened? Yeah. Earth was right there. I thought I could just go.
This guy hit me and now I can't find my way back home.
What the heck? Yeah. That's so crazy. Okay. So,
I was trying to come up with so many analogies, and one I came up with that I think is kind of crazy but kind of fun is, normally everyone throws those graduation caps up in like movies and stuff. I don't know what people do in real life. Yeah. You throw your graduation cap up and they all fall back down. getting into this triplet state where it's not supposed to be is as if we had a sticky covering on the ceiling. And so everybody throws their graduation caps up and they all get stuck and then they just one by one fall down over a very long period of time instead of it all happening at once. It's like, oh, something went wrong and now they're all stuck up there and it'll come back down, but it's just going to take a while.
Yeah.
And that was the most absurd. I was like, where did that even come from in my mind? I don't know, but I thought it was a funny visual.
Yeah. Yeah. That is very funny. That'd be such a funny like prank to play it on the students.
Yeah.
For like the faculty to do that would be like, we go to the ceiling with sticky stuff. And when they celebrate, they're going to just be stuck there waiting for their hat to fall.
Like fly paper, but
yeah.
Or like if that was against the rules and then if you threw it up, even though it was against the rules, it got stuck up there.
Yeah. It's like, and anyone who does that doesn't get their hat. So.
Because it was forbidden.
Yes, it's forbidden.
Forbidden.
Okay, should I start from the beginning?
Yeah.
Okay.
Yeah, I think so. I think we sort of did a little bit of a recap, but I think you explaining it to wrap it up would be helpful.
Okay. So we've talked many times before about the sort of general thing that happens in many different places and different ways about electrons getting excited up to a higher level, higher state kind of thing. And then they come back down. And the coming back down is typically what we are actually seeing as like light being given off or whatever thing's happening. It's not always light, right?
Sometimes it's heat. Yeah.
Heat, right. Yeah. Like is that what's happening when we're doing the remember the hand warmer thingies?
That's an exothermic reaction. I think a thing that we've seen. When is the time that we've seen this? Probably highlighters is like the best thing. It's like fluorescence is electrons being excited, re-emitting, and you're seeing that light reflect back. I know that we've talked about excited states before, but for some reason I'm blanking on when.
We talked about,
I know that we've talked about it.
We have several times.
Oh, one is sunscreen.
Oh, yes.
The organic molecules in sunscreen absorb the light and then they it like lets it back off as heat.
Right. Yes.
I just looked up excited states in my in my notes app where I make notes, but the chemistry behind the northern lights too.
Oh, yes. Okay, yeah.
Because they have like different levels of excited states where the oxygen can absorb light and So yes, excited states. We've talked about it. I feel like
even
a
more time.
lot.
Yeah, even more times than that. I'm sure if we look back, I'd be like, oh, duh, like this time and this time and this time. But that's normal. We've talked about it plenty of times. The difference here is we definitely got into the flipping thing, which is we hadn't really got into before that I recall. But so when these specific molecules that this can happen to, these electrons that can happen to, when they get excited and they're already in a certain spin from the get-go, and they get excited, they're up in their excited state, and while they're excited, something bumps them off course, right?
Yes.
Off of what would be the sort of typical pattern of get excited, come back down. Both things happen really fast. The up and down is happening quickly, right?
And what did you say about the spin again? Sorry.
So it's spinning, but whenever it's up in the excited state, that's when something knocks it.
Yes.
And flips it.
To the opposite spin.
Opposite spin.
Yeah. Maybe you can think of it as like going from clockwise to counterclockwise or something like that.
Okay. Got it.
That's the best thing I can think. I looked up it was an interesting Scientific American article, I think, of physical chemists trying to explain what the angular momentum of electrons really was. And they didn't really agree with each other. And they were having a really hard time putting it in everyday terms. And I'm like, yeah. So that's when I decided we could just think of it in terms of rotation.
Yeah. Okay. Yeah. And so while it's up there, it gets flipped. It was spinning one way, and then because of that, imagine even if I was spinning and then someone just somehow flipped me, now I'm spinning the opposite way.
Yep.
Basically. And then as it's trying to come back down, it can't quite follow that fast path anymore.
Right.
That we normally see in like any other things that are coming down from their excited state quickly. So now this electron is having to find a different way down, and at some point during its way down, it flips back to the way it was supposed to
Yes.
be spinning.
Yes.
And then does eventually, after time, get back to its, what'd you call that state again? Resting state or?
Ground state.
Ground state.
Yeah.
Yeah.
And I will say, so something my husband and I talked about is like, I don't know if the actual transition of it finally getting to go back down to its ground state, I don't know that that transition itself necessarily happens slowly. It's just that it's not all the electrons at once, I think, is what it is. It's we're just letting a trickle of electrons out instead of like them all falling at once. That's why it's not so bright. And that's also why it takes so long, is because the same number, got excited.
Yes.
But they're just being released slowly instead of all at once.
So because of that, the like sort of the path not being as neat, it's sort of creating like a congestion of sorts.
Yeah.
Like they're all preventing each other from getting a good, easy path down kind of thing.
Yeah.
So maybe it isn't like it's not like insanely long, but it's like all these electrons are trying to be like, what the heck? What happened to me?
Right.
Why am I upside down? I don't know what's going on. They're all like, ah.
Yes, exactly.
And they're bumping into each other and they're, yeah. Okay. And so then we get this low level glow.
Yeah.
Well after it was exposed to light that got it excited in the first place.
Which is weird because oftentimes the levels in the excited state don't line up to where that can happen very effectively. And that's why most things don't glow in the dark. That's why it's special that some things do, is because it's rare. So rare that it's sometimes called forbidden.
Interesting.
And it's kind of spooky that it's allowed sometimes.
So it's like because they did that and like because it's forbidden, it's like a curse. They're doomed to have to glow longer than they normally would have.
And that's your spooky chemistry. But really the spookiest thing of all is how hard it is to understand physical chemistry. You know what I mean?
Yes.
That's the thing that's going to be spookiest this Halloween, is just think about physical chemistry.
Yeah, that is really scary. Hopefully
Physical
you guys aren't
chemistry
listening.
is like...
I hope y'all aren't listening to this too late at night.
Yeah, I'll just keep you up at night. There's a joke in the chemistry world with like a bumper sticker that's like, honk if you passed P-Chem, because it's so rare to find anyone else who did. It's like it's just a hard, weird class. So even our friend in real life, Ronnie, he talks about, he still remembers to this day. He's like in his 60s and he's like, yeah, I remember we had like weigh air. And talks about how weird of a class P-Chem was, and it was weird.
That's so crazy.
Yeah.
Wow.
So, and then I already mentioned the names of the ones. They have like impurities built in, and also zinc sulfide is another one. And so I think that's all the fun facts. I did forget to write the phosphorus one, but maybe I can include that in our next bonus episode.
Okay, deal.
So, instead of just talking about something that made us happy this week, lately we've been doing some categories. And I thought of a really good category is, what is your favorite glow-in-the-dark nostalgia thing?
Ooh, favorite glow-in-the-dark nostalgia thing. Well, I will tell you that the very first thing that I thought I would talk about glow-in-the-dark is that I remember when I was a kid, we moved into this house when I was in second grade, and I got the chance to like choose some decorations for my room. So I chose, this is back when, so there was a time when wallpaper was in, and then it was out, and then it came back in again, I think recently. So, I'm not keeping up with that stuff. But back then, we were doing like wallpaper borders along the like top, you kind of do that kind of stuff where it wasn't really wallpapering the entire wall.
Yeah.
I chose this space one that kind of made it look like you were looking out of like a very sort of narrow window out of space. Obviously, it repeated.
Wow, that's cool.
All the way around the border of my room. And then I got a bunch of glow in the dark moons and stars, and put them all on the ceiling of my room.
Yep.
And with some little tacky kind of stuff or whatever. And so whenever obviously I couldn't see the wallpaper when I turned the lights off, but I did get this effect of looking up and seeing glow in the dark stars and lots of moons, which, we only have one and that we can see.
Who's being picky?
Yeah.
How could you tell, were they moons? Were they crescents?
Yes.
Not like just circles.
Right. I don't think any of them were just circles. Yeah, crescents. and but mostly stars, I think. And yeah, I remember those very, very well. I immediately pictured them, and just like the cool effect of like being in my bed and looking up at the ceiling at night. And of course, it would fade over during the course of the night.
And now you know it's because it ran out of electrons trapped in the excited state and no light to.
It's funny because usually I was asleep by the time that would happen, you know, so it's kind of funny how like it's kind of perfect because it's a cool effect right as soon as you turn the lights off.
Yeah.
And then it would be maybe actually annoying if it just stayed glowing the same level the whole night.
Yeah.
And so
it's
the fact
like
that it
works out well.
Yeah.
Almost like a nightlight only at the beginning.
Yes.
Recently my best friend from first grade, we're still friends, which is crazy and pretty cool. I'm like, I've known you for like the fraction of my life that I've known you is always getting bigger. You know, it's like those first 5 years of our life when we didn't know each other. She recently sent me a message that was like, you had to be there. And it was like pictures of those glow in the dark stars and then door beads. Do you remember?
Yes.
Yeah.
I had door beads that were also glow in the dark.
Oh.
And were moons and stars.
And you're nice. Yes. Oh, I feel like I knew somebody who had those.
Yep. Mm-hmm.
And you remember that blow up chair that some people had in their room that looked like almost like a lounger? Yeah, she sent me a picture with like those things. And maybe that's what inspired this episode a little bit. Not intentionally, but so it's funny that those glow in the dark stars, that was like one of the first things that I think of. I think my sister also had like a dolphin that was a similar glow in the dark, but also with stars in the package, like on her headboard. But the first thing I thought of was I loved the Phantom of the Opera, which is a weird thing to love, but my mom listened to it all the time. And then that movie came out in junior high.
Yeah.
And so I'm pretty sure then my best friend at that time in my life, Becca, got me a Phantom of the Opera shirt that had like a rose and a mask, and the mask was glow in the dark.
Yeah.
It was really cool.
That's cool.
That was my nostalgia. I feel like there was other really cool glow in the dark. I loved glow in the dark things. I thought they were so special and cool. So,
that's
but
awesome.
the first thing I thought was the stars and then that shirt.
Yeah. I think that's cool.
Nice. So comment your favorite glow in the dark nostalgia item. Or maybe you have a current glow in the dark item that's cool.
Yeah.
Hey, you know?
Yeah, totally.
I do have a current glow in the dark item that's cool.
What is it?
So we recently went on a camping trip and I listened to that podcast Tooth and Claw, and I learned all about bears and using bear spray. And so we got our bear spray and we'd hiked with it a bunch, but the first time we were camping with it, we like kept it. You should always keep your bear spray in the same place in your tent, or we slept in our car so that you could easily grab it if something happens. So that you don't have to waste time looking for it. But so we got all snuggled in bed, and, you know, it was like really dark in our car. And I opened my eyes and realized that the safety on the bear spray glows in the dark.
Whoa.
So that you can see it. Yeah.
That's smart.
But obviously it doesn't last all night. But if you've been like out there hiking all day, you know, it's been out in the sun. So it's just like a little safety feature that looking at it, I didn't notice. I just thought it was like a, you know, cream colored piece of plastic. But that was like a little recent, like, this glows in the dark. That's so smart.
That's awesome.
So
wow, that's very smart. It's cool that they just like put that little extra like, this might help.
Yeah.
Especially thinking like, in those earliest moments of nighttime where it's like, this will be the strongest it's going to be. It's like, twilight, you know, sun's fading fast.
Yeah.
You might, I don't know. That's crazy. That's cool.
Yeah. So comment your favorite glow in the dark thing below in the comments, or on our Instagram, or wherever you want, so that we can hear about your favorite glow in the dark thing.
Yeah, I don't think I have a current one. So, man, that's cool. You have one.
Yeah. I was like, I know there's something. I was like, that's so cool recently.
Yeah.
That's what it was.
That's awesome. Well, if you have a thought, question, idea, either about this or something else you've wondered in your life, is this chemistry? Please reach out to us. Let us know what it is. Chemforyourlife.com. And you can share your thoughts, ideas with us. Maybe in a bonus episode. It might turn into a full-blown episode. Who knows? But we'd love to hear your thoughts and ideas. If you'd like to help us keep our show going and contribute to cover the cost of making it and keep it free, you can join our super cool community of patrons, patreon.com/chemforyourlife. Folks over there who support the show, they get extra special things for us to thank them for keeping the show going. Behind the scenes stuff, little videos of us being dumb, thank you notes and coffee hour, just stuff like that, and an ad-free version of the show, ad-free feed of the show, just as a way of saying thank you. So if you'd like to join and support the show, keep it going, keep it free, you can do that at patreon.com/chemforyourlife. But if you're not able to do that, you can help us by subscribing in your favorite podcast app, rating, writing a review on Apple Podcasts or Spotify, subscribing on YouTube. Those things help us to share chemistry with even more people.
This episode was made possible by our financial... Nope. This episode was... Nope. What just happened? This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. Believe it or not, I was looking at the page where this is written down, and still that happened to my brain. Jam Robinson is our producer, and the episode was only possible because of our amazing financial supporters on Patreon. We are so grateful for your support and for your excitement about chemistry and Chemistry for Your Life, making it accessible to even more people. Those supporters are Autoclave, Chelsea M, Dorian V, Scott B, Jesse R, Sierra L, John T, Avishai B, Bree M, Brian K, Carol R, Chris and Claire S, Chelsea B, Derek L, Elizabeth P, Emerson W, Hunter R, Jacob T, Christina G, Katrina H, Latila S, Lynn S, Melissa P, Nicole C, Rachel R, Sarah M, Stephen B, Suzanne P, Timothy P, Venus R, Erica B, Cullen R, and Jeanette N. Thank you all so much for everything you do to make Chemistry for Your Life happen, and for commenting and sharing on our Patreon page. It just is so helpful for us to know that you're there and excited for us.
If you'd like to learn more about today's chemistry lesson, you can check out the references for this episode in our show notes or in the description of the video on YouTube.
Spooky Halloween! Spooky chemistry!